All right, let's jump right into this. Welcome to the Explainer. Today, we're tackling what is honestly a massive hurdle for so many science students, the Cambridge IGCSE 0625 physics exam. Specifically, we're looking at how to completely master questions on force, weight, and gravity. But listen, we're not just going to sit here and run through a boring list of formulas. No way. Today, we're adopting a completely different mindset. We are going to look at your exam strategy through the lens of a paleontologist. I know, that sounds kind of out there for a physics explainer, but trust me on this. By the time we're done, you'll see exactly why this is literally the ultimate method for dissecting tricky exam questions and squeezing out every single mark.
Now, take a look at the question right in the center of the screen. This completely flips the traditional way we learn physics right on its head. Instead of starting with dense textbook definitions and abstract math, we start with a real-world question. What physical effect, measurement, or prediction actually depends on understanding force, weight, and gravity? Our source material calls this an application-first approach, and it's a real game changer. A strong study session shouldn't make these concepts feel like random decorative facts you just have to memorize for a test. It should make them feel absolutely necessary. Because physics isn't just about regurgitating words on a page, right? It's about predicting real-world outcomes. If you start your revision from this angle, you become way less dependent on memorized wording and so much more capable of reasoning your way through those weird, unfamiliar exam scenarios.
And that brings us to our core strategy. Think about it. When a paleontologist finds a fossil, they don't just grab it, rip it out of the ground, and toss it in a museum display. They carefully dig through the layers, they analyze the surrounding rock, they reconstruct the dinosaur bone by bone. Well, when you sit down for your Cambridge physics exam, you need to do the exact same thing. You must carefully dig through the layers of the physics question, rather than just doing a brain dump of raw, unfiltered facts onto the page, just hoping something sticks. Examiners see right through that. They aren't looking for a data dump. They want to see a carefully reconstructed answer that proves you actually understand what's going on. So how do we actually dig? Let's look at this three-step sequence. It shows us how to build our understanding from the ground up, and it's honestly a brilliant way to approach any new physics concept. You start with everyday language. Just describe what's happening exactly like you would to a friend at lunch. Then, step 2, you move to a concrete example, something tangible you can actually picture in your head. Only then, at step 3, do you bring in the heavy physics vocabulary and the symbolic math. If you jump straight to the complex formulas before you understand the concrete reality of what you're even talking about, well, you're building your knowledge on a seriously shaky foundation. Okay, so you're definitely going to encounter a lot of graphs in physics. It's unavoidable. And the specific elements listed here brilliantly highlight what examiners are actually hunting for. They don't just want you to read numbers off an x and y axis. When you're using graphs, you absolutely must explain the physical meaning behind the geometry. Like, what does the slope actually represent in the real world? What is the physical significance of the area under that curve? What is the direction or just the overall shape of the line? Tell us about the forces at play. If you just describe a line going up or down without connecting it to the physical reality it represents, you are literally leaving major marks on the table.
So the absolutely crucial point here is how we synthesize all this into a reliable system for the exam. According to our source material, this 4-step sequence is the safest method for structuring your answers. Think of it as your guaranteed blueprint. First, identify or define. Second, state the relationship. Third, explain the physics. And fourth, connect to an application. This sequence is a lifesaver in IGCSE-style physics because the top-tier answers, the ones that get the best grades, consistently demonstrate both deep theoretical understanding and practical application. Let's break these down layer by layer.
Steps 1 and 2 act as the bedrock of your paleontological dig. First, you firmly identify the core quantity or phenomenon the question is asking about. Don't leave the examiner guessing what's in your head. Name it clearly. Then, you state the specific relationship or equation involved. This is where you bring out your formula or your governing principle. But remember, this is just the foundation. Stating the equation proves you brought your tools to the dig site, but it doesn't prove you know how to use them in the dirt. To do that, we need the next step. Now, this is where the real magic happens. Step 3 is all about explaining the physics, and you do this through a strict cause and effect chain. This is absolutely vital, especially if the topic involves fields, forces, circuits, or waves. You must insist on cause and effect rather than just listing out isolated facts. You have to prove the underlying physics by sequentially linking an initial action, like a force, directly to the final physical outcome. It goes like this. Because A happens, it causes B, which results in C. It's like setting up dominoes. If you break that chain or skip a domino, the whole explanation just falls apart. And finally, we hit step 4.
You've got to connect the physics to an observation, an experiment, or some real-life device. This is closing the loop right back to our application-first approach from earlier. Why does this matter? Because you should always be able to name at least one real-world situation where the concept actually matters. Exam questions love asking you to describe a practical use connected to force, weight, and gravity. If you can't connect your beautifully structured cause and effect chain to the real world, you haven't fully grasped the whole shebang.
Just look at the sheer scope of the fields listed here. It makes you realize that force, weight, and gravity aren't just confined to some boring classroom whiteboard. Depending on what you're studying, these ideas pop up in engineering and safety protocols, transport systems, global communications, crazy advanced medical tech, and of course, astronomy. You should always be aiming to explain how physics helps us predict or improve outcomes in at least one of these areas. It brings those abstract, dry symbols completely to life. But hey, even the best paleontologists mess up if they rush the dig. So let's transition to analyzing the common weaknesses that cause students to needlessly bleed marks. I like to call these brittle fossils. These are answers that might look okay at first glance, but the moment an examiner applies a tiny bit of scrutiny, they completely shatter. You really need to be careful here. Our source highlights 3 specific traps we need to avoid at all costs.
Here is the first brittle fossil, flawed. Writing a correct formula all by itself. You might quickly jot down W equals mg and think, boom, nailed it. Actually, scratch that. That's exactly what you shouldn't do. The safest method is defining and explaining all the variables in that formula. What exactly is W? What does M represent? What is the physical meaning of G in this very specific context? Dropping a naked formula onto the page without explaining the variables is a classic, painful way to miss out on easy explanation marks. You always have to translate the math back into physics.
Now let's see how this builds into the second trap. Flawed. Quoting a process in isolation. You might be able to perfectly recite a memorized definition of a process from your textbook, but if you don't link that process to a clear physical effect within the actual system you're analyzing, that's an incredibly brittle answer. Examiners want to see that you understand what the process actually does. Always follow through to the physical consequence. And here's the final common trap. Flawed. Naming an example randomly. If a question asks for an application of gravity, you can't just write a roller coaster and happily move on to the next page. Nope. The safest method requires you to justify exactly how the physics drives that example. You have to show why it follows from the physics you just spent time explaining. Remember our 4 steps? The application has to connect directly back to the cause and effect chain. Just dropping a random noun won't cut it. So how do we lock all of this in our brains for exam day? This table right here is your ultimate reconstruction tool. It gives you 4 memory prompts. When you are revising, you need to ask yourself these 4 questions for every single topic. 1. What is the core idea? That hits your definitions and rules. 2. What changes physically? That forces you to build your domino cause and effect chain. 3. What quantity or graph shows it? That locks in the math and the relationships. And 4. Where is it used? That guarantees you understand the application. Our source explicitly states that if you can answer those 4 prompts out loud, the topic is usually secure enough for those tough, structured questions. It is literally your ultimate checklist. So, we've dug through the layers. We've seen exactly how to reconstruct an answer from the core definition all the way up to the real-world application, while avoiding those brittle traps that just break under pressure. I want to leave you with this final provocative thought. If you were handed a completely unfamiliar device right this very second, could you use this 4-step method to explain the forces, weight, and gravity making it work? Because at the end of the day, that is the true test of your knowledge. Don't just memorize the past papers. Learn how to dissect the physical world around you. Good luck with your exam prep and keep digging deeper.